e-conference. It's a daily webinar series. For today's session of the dais is Honorable Miss Saranya M Ma'am. So I heartily welcome to you, Madam, in today's session.
Thank you, sir.
I welcome the chief organizer of an international e-conference, the ideal principal of Sri Kumar Swami Mahavidyalaya Ausa, Honorable Dr. M M Betkar sir. I also welcome all those dear attendees. The topic for today's presentation is function and relations in mathematics. The topic is going to present, as I have mentioned, today's keynote speaker, Honorable Miss Saranya Ma'am. She is serving as an assistant professor at the Department of Mathematics. She is from School of Physical Science, Marudhar Kesari Jain College for Women, which is autonomous college from Vaniyambadi, Tamil Nadu State, India. So with this brief introduction, now I request to you, Madam, please start your presentation on the topic function and relations in mathematics. You are most welcome.
Thank you so much, sir. Good evening, everyone. Today I'm going to talk you about function and relation in mathematics. So this is what my topic. I'm Saranya, assistant professor in mathematics. I'm working in Marudhar Kesari Jain College for Women. So these are all today's topic which I'm going to talk to you about these topics. Introduction about function, its representation, types of function, application and its sets. So Dirichlet, actually he's a mathematician. His contribution in the field of number theory, analysis and mechanics. Actually, in 1837, he first introduced the concept of the function with the notation y is equal to f of x. The concept of relation is a well-framed rule. There is a relationship between minimum two sets. There is a connection, there is a bond between two things. That is called a relation. And function is well-behaved relation. So this is called the function. So exactly the point where we have to go, that is a well-framed condition, is called the function. Let's see through some examples. So representation of the function can be represented as set of ordered pairs, tables, arrow diagrams and graphs. But I am going to share you about in ordered pairs and arrow diagrams. So examples of relation. I'm taking people height and their names. It's an example of relation. I'm relating those together through an ordered pair like height and name or name and height. This is called an ordered pair. These two are considered as set. The first one belongs to the first set and the second thing belongs to the second set. So I'm connecting those sets together, a person's height and their name. I'm relating those together. It is a relation. Not every relation is a function because function, it has a condition. I'm telling you about the function later. Now a relation is a set of ordered pair. I'm showing you in ordered pair. See this. This is an example of it. So these are all called ordered pair. The first elements 2, -1, 4, 9, zeros are all called domain sets, home set. And the second elements 3, 5, 2, 9 and -6 are all called codomain sets. Codomain sets elements. Okay, this is called a range. So there is a connection between those two elements. Here the relation is integer. Those elements are all related with the condition of integer. Now I'm taking an example and this is called domain set and this is called the codomain set. I'm relating the elements of the domain set to the codomain set. One is related with 6, 2 related with 2, 3 related with 4, 4 related with 8, 5 related with 10. Here these elements are represented in ordered pair. Here 1 comma 6 is a one element, the one bonding between those two numbers. The left side is domain, the right side is codomain. So I can get totally 5 elements in this relation set. Now I'm talking about a function. Function, not every relation is a function. Every function is a relation. Why? Because there is a definition for function. X and y should be a non-empty set. A function from x to y is a relation that associated with each element of x exactly one element of y. This is the keynote of the function. There is exactly one bonding between those two elements. See, so this is I am considering those two as a domain set and codomain set, and I am taking two elements from those. So this is a domain set and this one is codomain, and this element is called as a pre-image of 4. So it is a pre-image of the element 4, and this is called image of 4.3. So I'm considering that mapping F is from R to Z. R means the real number 4.3, which is converted to integer number 4. So this is a function I'm giving through an arrow diagram. I'm taking another example. This is what the rule, the relation I'm giving, that function f of x is equal to x square. Let's see is satisfying the condition of function. I'm taking two sets. Set A is a domain set and set B is a codomain, that is also called range. I'm connecting the element of 1 with 1, 4 with 16. When I'm substituting these elements x, I'm substituting 1 in this x, I'll get the output 1. When I'm substituting 2, I'll get 4. I'm substituting 3, I'll get 9, 4, 16, 25. So the connection will be like this. 1 is mapping with 1, 2 maps to with 4, 3 maps to with 9, 4 maps to with 16, and 5 maps to with 25. This is what the mapping for the given function. Let's see, is that satisfying the function's condition? First one, the elements, all the elements are related with the codomain elements. Yes, all the elements are mapped. The next condition, the all elements has only one relation. Yes, it doesn't has more than one relation. Exactly, each has one relations. Yes, it is also true. Then it is called a function. The next one, I'm considering the domain set is girls and the codomain set is grade. I'm relating those together now. 1 related with 2, 2 related with 1, 3 goes to 8, 4 is for 6, and 5 is for 4. Is that a function? Let's see. The first thing, 2 is again goes to 4. So let's 4 to 4, 2 to 2, 5 to 1. And is that a function? No. Why? Because the first condition, every element of the domain set definitely having the relation with codomain elements. But here the 3 doesn't have the relationship with the codomain elements. The first condition is false. So this is not a function. Let's see another example. Here 3 maps to with 2, 3 maps to with 1 maps to with 6, 4 maps to with 4, 2 maps to with 2, and 5 maps to with 1. See, here 2 and 3 both having the same image. Is that a function? Yes, it is. Why? Because every element of the domain set is related with the elements of codomain set. The first condition satisfying. The second condition, every element should has exactly one relationship with the codomain set. Yes, it has one relation and it also has the same one relation, the equal number of relation. So it is a function. So this is an arithmetic example of a function. I'm taking the first function is 2x and the second function is x square. I'm adding those two functions together. I will get this as a result. When I'm producting those two functions, I will get this as a result. This is an arithmetic representation of a function. Okay, so function notation. Actually, this f is a notation of the function, and the second one x is the element which belongs to the domain set. And the right hand side, the solution, the output element which belongs to the codomain set. This is the notation of the function. The domain is R and the codomain is also R. So now we are going to see about the types of function. This is a condition of one-to-one condition. A function which should satisfy x is equal to y, that means a domain set. The output, the f of x is also equal. If it is equal, the output is also equal. If it is not equal, the output is also not equal. This is what the exact condition for one-to-one. Let's see the example. The one-to-one condition concept is this is the main concept. Each element in the domain has unique image. So this is the keyword, unique image in the codomain. See this example. So this is a domain set and this one is a codomain set. So here in the domain set, every element are having a unique image, different image in codomain set. So this is an example of one-to-one function. See this one is that one-to-one about the codomain set. We only consider about the domain set. Every element should be mapped onto function. So onto function means each element in the codomain is the image of some pre-image. It should have some pre-image in domain set. See the example. Here we have to consider this codomain. The codomain set, every element is mapping with the domain set. Okay, it at least has one element. It may have more than one element also. Okay, we just see every element are mapped and every element at least has one image. Okay, see this condition is satisfied. It is a onto function. See here, there is a two elements left out. That doesn't have any pre-image here, so it is not onto. And onto function is also called subjective function. And we can use multiple elements in the codomain also. That is more than one image, pre-image also it can have. See here, the element 2 has two pre-image. So it is also accepted in subjective. And the relationship between one-to-one onto is, see, compare the based on the definition of one-to-one and onto. In one-to-one, we only follow the domain set. Everything are mapped. Yes, it is mapped. Everything has unique image. Yes, one has one image, two has different, three has different unique image. The one-to-one condition is satisfied. But see, the onto condition is that, is it satisfied? See, every element, is it mapped? No. The second element is left out. So it is not satisfying the onto condition. Hence, the given example is one-to-one but not onto. See the second example. The domain set, everything has unique image and the elements of codomain set is also having at least one pre-image in the domain set. All the things are mapped. So it satisfies one-to-one as well as the onto concept. Hence it is one-to-one and onto. The third example, it is mapped with every element are mapped, but the first element and the third element is mapped with the same thing. So both the elements having the same image, but it is a wrong case for the one-to-one condition. So it is not one-to-one. And as well as C, in onto every element should map with the elements of the domain set. At least it should has one pre-image, but the fourth element doesn't map with any of the domain elements. So it does not follow any of the condition of one to one and on to. So it is no one to one and not on to. Bijection means the function which satisfying both the condition one to one as well as on to. The condition satisfied means then the function is called bijective function. See this example. The one to one condition is also satisfied, on to condition is also satisfied. Hence this function is called bijective function. And this is also called one to one correspondence. Identity function. Yes, the mapping with itself. That is, the domain set as well as the codomain set both are equal means it is called identity function. For example, f of x is equal to x. If I'm taking the relation f is a mapping from R to R, I'm taking every element of this set to this set. F of x is equal to x. This is a condition, f of x is equal to x. When I'm substituting 1, I'll get the output 1. When I'm substituting 2, I'll get output 2. When I'm substituting 3, I'll get 3. So all the elements mapped with itself. So it is called identity function. See another example. I'm taking this domain and codomain. The condition is f of x is equal to 4. It is a relation. I'm framing the rule. Okay. So domain set is or, codomain set is or. Now I'm creating this function. What will be the output? Let's see. So R means it's having infinity of number, but generally I'm considering from 1 to 5. So when I'm substituting 1 here, I'll get the output 4. When I'm substituting 2, I'll get 4. When I'm substituting 3, I'll get same 4. So infinity times I'm substituting, the same answer will become. So 1 maps to with 4, 2 maps to with 4, 4 maps to with 4, 5 maps to with 4. All the elements mapped with the same elements. So this is called a constant function. Next, composition of function. So we have minimum 3 sets. 1, 2, 3. So 3 sets at least minimum we need for taking a composition. I'm framing the function g from first set to the second set, and another function second set to the third set. I'm taking an element A. So the element mapping with the second statement, that will become g of A. I'm representing the function g, that's why that become g of A. And the third thing is f of g of A. So for example, I'm considering in real life example, the relationship I'm framing, that is friend. Okay, friend. Here also I'm taking that is friend. So the A friend is related with the B friend, and B friend related with the C friend means automatically the first person will be related by a friendship relation to the third person C. So this is denoted by the symbol of composition F, composition G of A. So this is an arithmetic example of the function, composition of the function. I'm taking the first relation is 2x plus 3 and the second relation 3x plus 2. And relation R is from real set R to R. Okay. The first element is 1. So when I'm substituting this 1 to this equation, G of 1, so 3 into 1 plus 2 will become 5. The output is 5. The next thing, I'm substituting the G of 1 value in the equation f of G of 1. See here, I'm solving that. I'll get the value of 13. So this is also belongs to the real number R. So all the elements which belongs to the R set, and this is called the composition of the function. So here I'm working that problem. So the final result is 13. Some of the application of function is the mathematical building blocks for designing machines, predicting nature disaster, curing disease, understanding world economic, and for keeping airplanes in the air. Functions can take input from many variables but always give the same output unique in that function. So let's see some example problems for the function. Burglars robs a bank, escape in a car. They pursued by the police. The good news is they took a photo, but the bad news is the photo which is blurred. They approached a mathematician. He can help by giving a function in a transformation equation. They used a transformation equation for solving the blurred image to the original image. So like this is an example of it. You can convert the blurred image into the process of the transformation function, and he will get an output as an original function. Some more applications of it. It is a blurred image to a clear image, and the output of the lines in pixels. So the next final topic is sets. So set, I'm taking a particular concepts of the intervals, power set, universal set, Venn diagram, union and intersection of the sets. So before entering into the sets, we should know about the intervals of it, the open interval and the closed interval. So open interval means it lies between A to B, but it shouldn't take the exact A and B. Okay, so closed interval means I can use the A as well as with B. It should be used in box bracket. So these are all types of intervals. I can use both open, both closed, or open closed, close open, both open. So I represent the intervals in a line number. Here I'm excluding the intervals. It is excluding A and B, and it is including A and B, excluding A, including B, including A and excluding B. Okay, this is a definition of the power set. Power set is all collection of all subsets of the set. If I'm taking the set is equal to 1, 2, the power set is the collection of all the subsets of it. The subset means 1, it's a separate subset, 2, subset, 1, 2, the set itself is a subset, and empty set is also a subset of it. So the collection of all the subset is called the power set of the given set. And the number of power set is calculated by 2 power m, number of elements of the given set. The universal set, and it is a basic set, and it is represented by U. Let's see some example. I'm also given some Venn diagram for clear view of it. Union of the set. First, at least we should have minimum 2 non-empty set. So I'm taking that is A set and B set. When I'm taking the union of this, I'm shading this in different color. So I'm adding those 2 elements which belong to A or B. Either A or B, I have to write the element in it, A union B. So this is a definition of the union set. This is an example of it. I'm considering A is equal to 2, 4, 6, 8 and B equal to 6, 8, 10, 12. I'm taking union, whether the element which belongs to A set or B set, I should write the name of it. So 2, 4, 6, 8 I wrote, and here 6 and 8 already appeared in A set. No need to repeat it again here. So I'm taking 10, 12 again. So this is an A union B. So it is an alphabetic letter. So this is what the solution of it. A, C is repeated already here. So the answer of it is equal to A. So this is an intersection of 2 sets. I'm considering the set A and B. The intersection means the common meeting point of A and B. So here I shaded the portion of the common points. See through the example, and it is and A with the element which belongs to A and B. So see the numerical example. The common points are 3, next 5, and then 7. So these are all common points. So I wrote A intersection B is 3, 5, and 7. This is a subset of B. It is also a subset of B, and the intersection is equal to B when we are comparing the result. So these are all some properties of the intersection of the sets. The commutative law is satisfied, associative law, and the law of empty and universal, idempotent law, and distributive law. This is an Venn diagram. Distribution of intersection over union. So B union, I'm taking 3 different sets here. B union C means I'm shading B along with C alone, excluding A. A intersection B union C means the intersection portion, the common meeting portion of B union C along with A. So this portion alone I'm shading here. So the next A intersection B means A set B set meeting point. A intersection C means A and C common meeting point, and both the union of the set. So the common point between those two is not common point, element which belongs to A intersection B or A intersection C. So both together I will shade here. So these are all some more formulas based on the sets, union and intersection. So those formulas we use to solve the problems. For example, I'm considering a problem. In a school, there are 20 teachers who teach mathematics or physics. Of these, 12 teach mathematics and 4 teachers both physics and mathematics. How many teachers physics? I'm considering those maths or physics is equal to 20, the number of mathematics teachers 12, and maths as well as physics is 4, and I'm going to find the result for how many of them are going to teach physics. I'm substituting those results in a formula. I'm solving those formula. I'll get the result, that is 12. So today we learned about the relation function rates. Thank you.
Thank you so much, ma'am, for the wonderful presentation.
Yes,
Now I
ma'am.
request all dear participants for your queries. If you have, please come ahead and discuss with keynote speaker, dear participants.
Okay, sir.
Thank you, ma'am.
Thank you, ma'am.
I had come to your college last year. I think I had to give a presentation.
Oh, okay, ma'am. Thank you, ma'am. Thank you.
It was Minas Banu. They all invited me.
Oh,
Good
okay, ma'am.
presentation, ma'am. Can
Thank you,
we
ma'am.
get the record of your presentation?
Yes, sure, ma'am.
Okay, thank you. Thank you.
I think ma'am have explained in a clear-cut way all the things you have cleared. So there is no question. Now I request the chief organizer of an international conference. Yes, sir. Yes.
Thank you very much, ma'am. Of course, the mathematics is really tough for me, at least, and that is why I turned to medical field. And definitely, it requires too much of efforts and patience to learn this science. And I remembered one of my patient went to US because of mathematics. She was very wonderful in a great in our mathematics. So thank you very much for your presentation today. And we went back again to the mathematics. I remember my 12th class. Thank you.
Thank you so much, sir.
Thank you,
Thank
sir.
you. Thank you, sir.
We get more about it, reminding about it, and how mathematics is used in application. You have said that the blur image can be cleared. So every function, every relation and mathematics equations are used in the technical field so that they are acting on that, because mathematics is every time we have to measure, we have to count, we have to compare. So these things are useful in the this technology also, but they are used by the technicians, so we are unable to understand what the mathematics are using, but it's all depends upon mathematics. So thank you. You are new in this presentation field, but you have explained very nicely. Your PPT was very perfect. In future you will be invited here, and we wish all the best for your future academic collaboration. Thank you, ma'am.
Thank you so much, sir. Thank you.
Thank you, Dr. Saran Shukla sir. Thank you, Prashant sir, and those who are present here. Ugade sir, please express vote of thanks if possible.
Thank you, sir. Now I move towards the vote of thanks. Sri Kumar Swami Mahavidyalaya Ausa, District Latur. As we know, dear participants, we are organizing every day a series, internationally conference. For today's session on the dais was Honorable Saranya ma'am, who have expressed now on the topic functions and relations in the mathematics. Really, it was too knowledgeable session, ma'am. You have explained and covered all the aspects. Each and every concept you have cleared regarding the topic. So we are very, very thankful to you. You paid your valuable time to the series. I also thank the chief organizer of an international conference, Dr. M M Betkar sir. Especially thanks Dr. Saran Shukla sir, who always nicely interact with the each and every keynote speaker every day. And I should not forget all those dear attendees who have joined today's session. So thanks a lot once again to you all. Kindly request you all, please fill the feedback link which is given in the chat box. So with the kind permission of the chief organizer, I declare today's session is over. Thank you so much once again.
Thank you, sir. Thank you.
Thank you,
Prashant
ma'am.
sir, you are in journey, but still you actively participated and conducted this conference. So I am thankful to you, and thankful to Nagarjuna madam, who have also discussed here with the speaker. So thank you to all. Thank you. We will again meet again tomorrow. Thank you.
Thank you, sir.
You can leave, madam. No problem. Okay.
Okay, thank you, sir.